Okay, let's look at a covalent molecule. We're going to look at H2. Now, electronegativity, or En for short, is the desire for electrons. Desire for electrons. And in H2, if you look up the electronegativity for hydrogen, you would see that it is 2.2. You can find these all in Table S. I'm going to write that, Table S. So it's the last page of your reference tables. And both of these, they're both hydrogen, so they're both going to have an electronegativity of 2.2. Now, because they both have an equal desire for electrons, we say this is a non-polar bond. So it is symmetrical. That's a symmetrical bond. And because it's a symmetrical bond, we're also going to say that this is a symmetrical molecule. And so this would be a non-polar molecule, because that distribution of electrons, remember, each of these hydrogens is pulling equally on those electrons in the middle. We can also draw it like this. So these electrons are equally desired by both of the hydrogens. And so there's a symmetrical distribution of charge, or electrons, within this molecule. Let's look at another molecule where this is not the case. So we're going to look at HCl. So this is HCl. Now in HCl, let's look at the electronegativity of each atom, or En. Hydrogen, like we just said, is 2.2. But chlorine, if you look that up in Table S, you'll see that it has an electronegativity of 3.2. So here we have pretty different electronegativities. And so chlorine is going to have a stronger pull on these electrons that are shared between the hydrogen and the chlorine. And so a more accurate kind of depiction of this molecule would look more like this. So those electrons are being pulled towards more towards the chlorine. And you can represent this using something called a partial charge. So partial, we kind of represent the word partial using the lowercase Greek letter delta. And then because electrons are negatively charged, they're being pulled away from the chlorine, we say that the hydrogen has a partial positive charge. All right, so that's partial positive. And then because those electrons are being pulled more towards chlorine, the chlorine is going to have a partial negative charge. You can also show this using an arrow in the direction that the electrons are being pulled in. So electrons are being pulled towards chlorine. And then we just put a little kind of tail at the end of the arrow. So I like to see this tail as like a little plus sign. So that's where the positive charge is. And then the arrow points towards where the electrons are being pulled. Okay, and so in this molecule, this is not a symmetrical bond because these electrons are being pulled towards one end. And so this is a polar bond. And because of that, because of the distribution of electrons within this molecule, they're not all equally like surrounding the atoms. We say this is a polar molecule. So it's an asymmetrical bond and an asymmetrical molecule. Okay, let's look at another example. So we'll look at water. And in water, this is a more bent molecule, so it looks like this when drawn out. Now, hydrogen, again, has an electronegativity of 2.2. Oxygen has an electronegativity, however, of 3.4. So those electrons that are being shared between the hydrogen and the oxygen are going to be pulled more towards oxygen. So I'm going to draw my arrows showing the pull of the electrons in the molecule. I'm going to draw my positive tails. And so those electrons are clearly being pulled towards one end of this molecule. And so if I draw my partial charges, the oxygen will have a partial negative charge, and then each hydrogen will have a partial positive charge. All right, and so this would be considered a So each bond is a polar bond because it's an uneven sharing of electrons. And then the molecule itself is going to be polar as well because there's an uneven kind of distribution of charge around that central atom, or around that oxygen. So there's clearly more positive charge on this end and more negative charge on this end. And so there's the entire molecule itself becomes asymmetrical, and it becomes a polar molecule. All right, let's look at another example. So we're going to look at NH3. All right, so here's an example of NH3. Now, hydrogen, again, electronegativity is 2.2. All these have 2.2 for their electronegativity. Nitrogen has an electronegativity of 3.0. And so those electrons that are shared between the hydrogen and the nitrogen are going to be pulled more towards the nitrogen because it's more electronegative and has a stronger desire for electrons. So I'm going to draw arrows indicating the pull of electrons within this molecule. And they're all going to be pulled towards that nitrogen atom. And so my nitrogen is going to have a partial negative charge, whereas my hydrogens will also have, these are going to have partial positive charges. So the bonds, or each bond in this molecule, is a polar bond. And then the molecule itself, you can see there's more negative charge on this end of the molecule, and then on this end of the molecule there's a more positive charge. So this is an asymmetrical molecule, and so this is also a polar molecule. All right, let's look at an example of when you can have polar bonds but a nonpolar molecule. So we're going to look at CCl4, carbon tetrachloride. So carbon tetrachloride looks like this. Oops. Don't need that one there. And don't need these. Okay, so here's carbon tetrachloride. Now carbon has an electronegativity of I believe that's 2.6 actually. And then chlorine has an electronegativity of 3.2. And so because the chlorines have a higher kind of electronegativity, or that this range is outside of that 0.4 range, the electrons are going to be pulled towards each of the chlorines in this molecule. So all of those electrons are going to be pulled towards the chlorines. So each chlorine will have a partial negative charge. And then my carbon in the middle will have a partial positive charge. Now each bond within this molecule is a polar bond because it's an uneven charge. However, there's an equal distribution of negative charges around this entire molecule. And so because there's an equal distribution of negative charges around the whole molecule, we say that the molecule itself is non-polar or symmetrical. Let's look at one more example. So we're going to do CH4. CH4 looks like this. It's also known as methane. Now, hydrogen has an electronegativity of 2.2. Carbon has an electronegativity of 2.6. Now, because the difference between these two numbers is 0.4, whenever you have an electronegativity difference of 0.4 or less, we say those electronegativities are pretty much the same. They're equivalent. And so there's no partial charges here. There's no partial charges. And because there are no partial charges, we're going to say our bonds are nonpolar or symmetrical. And then the molecule itself is also nonpolar and also symmetrical.